two topics. One was a practical aspect, but we did discuss some practical aspects of the Hadoop implementation yesterday in detail, and so probably now you're probably more familiar with the issues concerning in implementing code, erasure codes in a general purpose software such as in Hadoop. So here we look at the main issue was that most of other researchers who worked with bigger clusters, they had an access to big data centers where the racks and other things are available directly physically. So which means that they have a more advantages in testing out even simple schemes. But whereas when other users, when these nodes are delivered through cloud computing technologies, then there are other issues come in. For example, where the nodes are located and what are the bandwidth and delay performance that affects the performance of these systems. So that was our thing. We try to do that. So the most of the theme of our the handling erasure coding is mainly from this aspect, actually working through that. So in this lecture we will look at issues that evolve out of geographically distributed storage clusters. And sometimes what might happen is that when you request for some service from a cloud provider, you might get some nodes from some location, some other nodes from some locations, and then you have your task to do and to be implemented on that system. So for example, in a Hadoop, you can run some other data analytics on it, but you get like that. In such situation, what kind of codes to be used, and so that was our investigation in this. And so this repair obviously will focus on the same idea concept, the main thing which is repair in these issues. So you already talked about the geographical issue, and one of the things that you might ask actually, is it not efficient to just to have your own data center and run all the functions such as, but sometimes for the purpose of reliability, apart from reliability that comes from the erasure coding, just reliability, you would like to have these data centers, the centers implement the code in different clusters. So just for example, even before coming here, there was, ours is a research cloud that whatever we showed in the Nectar, and we got an email saying that the sum of the nodes will be removed so obviously one particular cluster would be down. In such cases, it is the system should be able to automatically adopt and move over to another geographical location. So relying on multiple geographical location is a good idea. So that comes reliability, and I am not making any claim in actually the understanding the reliability issues pertaining to that. There are lots of rich work going on in such area. Just for example, how much of reliability you get by distributing this node to do this. So these are all that gets automatically repaired by using disasters that could happen. So for example, when there is a disasters happen to the network, then perhaps sometimes some of the nodes may not be available. So techniques pertaining to that are much more specific, and there are people use a lot of optimization areas in that thing as well. So so there is a lot of it's kind of huge volume of data, that resiliency that can be already there are people who attacking this problem through reliability by spreading their work around the different nodes, and that is an important research in itself. What we focus is when we have a general purpose cloud infrastructure available to us, and as we built a system like an Hadoop, and that what are the other interesting codes you could use, and how can you make the performance, how can you improve the performance in such geo-diverse environment. So and we focus mainly on the node failures, because that's the kind of things, node failures, and the important metric that we address is basically the delay and the disk IO and the bandwidth. So So at the end of this, after going through these LRCs and SOAR bus and all the three important codes that we use in our practical setup, I have already explained yesterday. So probably you are all familiar with how the code performs and its capabilities. So we will just, what we do is we actually show that this simple XR based one actually perform much better in this, and I present also in the first part of the talk of some results that we got through that, and also by working on it, and I'll post some problems, so that might help you to kind of look at the other problems. So this is the and we basically what we do is we have an XR based, I told you the MXR code, but what we did was we within the Hadoop is a big system engineered. It has a we can specify, for example, even though you have a different geographical clusters, I can now specify it as a rack and others, and you can tell the use the Hadoop saying that this is all these nodes belong to one rack, another rack, and then I can use this lack awareness property of the software to tune my code design. So we will compare the Facebook's RS codes with SOAR bus and others in these settings. So I'm not going to go in detail in this, but everybody is clear about it now. The MXR code. So basically it has 10 data blocks and parity blocks. What needs to be kept in your mind that basically this is each one is a node. You can think of that each one is a node, and when a block is written into it, so the stripe that you look for is a single horizontal stripe of 17 nodes, with out of which 10 are data blocks and the 7 are parity blocks. And this is and so obviously this will have a little more than storage overhead than RS code, but it will perform much faster in terms of this. That's the price you pay for this. So this is, I already talked about the making Hadoop location aware. So that's the kind of things, and this is this is kind of a rack awareness and can be done by a script. So you run some script and automatically the Hadoop will understand. So this is the concept that come out of the distributed systems, and I think Aaron has already explained to you how these kind of things work, and perhaps with your own some little bit practical work yesterday. I think you all spent about more than 2 hours. You probably have some kind of a first-hand information like how this system work, and so you can now start thinking of the issues that come out. So in fact, the whole erasure coding or this regenerative coding work where we start is actually looking at this practical setting. Okay, and what I also illustrated that other day with both the regenerative code, local codes, all of them actually come out of research centers who are heavily engaged with practical problems. That's why when they define codes, they keep changing the the nomenclature what suits better them for that system. So in a sense, that's the problem with such new areas. We're using some very age-old techniques, but when it comes through, it will introduce complications. And so one of the research, another objective of this course was also be able to kind of understand the papers in any modern papers in coming in this area. So having a little bit background on the coding, and so you should be able to appreciate the problems, and depending on your interest, you should be able to dig down and work through. So that's one of the objectives, and I hope that's what we address. The script file looks like that. This user script is a text file. It has just a machine and a pair, and you tell that some machine is in rack, some machine in rack, and we also look at the demo these racks things. We can So while placing blocks, Hadoop applies the settings and builds a topology in a hierarchical order. So that actually that will be this is the kind of property that gets adapted to this. And of course, if you don't specify this, and if you say these things are not there, then automatically Hadoop assumes kind of a random rack, or maybe put everything into one rack, and it doesn't distinguish this. So now what happens is, but basically we don't want to change whatever that Hadoop has, and one of the simplest things that we can improve performance by adding extra nodes that are parities. For example, if the parities are there, and in case of repair, invariably a new node will contact those parity nodes, right, wherever that is, and depending on where parity is there, then accessing them and the complexity goes on. So instead of that, one of the simplest idea which others people also thought about, what we thought about is actually parity duplication. So what happened if the actually parity for this block is in another rack, I just move it to this rack, or not move, sorry, maybe make a copy of that and available it to the locally. So which means that whenever some node fails, it will only contact the parity node in the local group, and hence it can recover much quickly. So this is the kind of things, this one default area. So because in Hadoop, and this basic idea is that, you know, when people design big distributed system, they want the underlying memory technology should be simple. So that way they can that way they can actually make this operating system work better. So in case, that's why when they had initially Hadoop, triple replication, you know, so normally let us say what happens is when you tell one, if you can't hear it, you maybe tell repeatedly many times, hopefully that person can get. The same idea replication, and as we all said it, you know, that's a use. So now we can just extend the replication to the raided area. So we're just, okay, add some more parities. Okay, so in fact, when you add more parities, of course, the this will probably add some locality into the geodiverse setting already. So for example, you may have some lot of data nodes, but parity nodes are limited, normally we do. So by adding extra parity to locally, so you get actually the same code now, maybe you get a second copy of the code, like in the sense that you can regroup those nodes that has a new parity, and that becomes a local code. So we took, for example, here what we do is store 2 replicas of parities with the aim of reducing the time taken reduction. So what we do is in case of Reed-Solomon code, we made replication, the parity is now doubled. So normally with Reed-Solomon code, how many you have? You have 10 data nodes, 4 parity nodes, you replicate it, it becomes 8. So totally the overhead becomes 1.8x. In Sorbas, if you replicate it twice, so the Torbas has 6, so replication will become 12. So in fact the parity, this will actually become like a low rate code once you replicate it. Okay, but it will be still better than the triple replication of a hard data one, and the MXR code, if you do, it becomes even more, 2.4, because you see already for every 10 blocks there were 7 data things, but when you replicate it you got 14. So totally it is 2.4. So parity duplication, this was achieved through changes in the configuration files. This basically, so the better block placement policy could result further improvement. So this is the, once you have this, at this point we have not taken care, where these block policies should be there, we just kind of left it aside. That's one of the parity replication strategies. So what is our test cluster? So that our test cluster, I think we already explained in the past. This is a Nectar research code. We have totally 45 nodes, and they got spread over 3 locations, and the master node is in the Tasmania sector. So we have if this is the picture of Australia, it's almost like a semi kind of a circle, and you see the Tasmania is just outside protruding. It's like a Sri Lanka to India. Yeah? So that's the place. One of the major things are located. Other one is in Melbourne. Other one is in I think there is one in Perth and one in Queensland. So so master node was there, but there are 3 other node locations along with the ping times also we mentioned here. For example, here if you read ping times between Tasmania and Melbourne is 0.7, between 0.7 millisecond, between Brisbane it is 37, but this with the longest is with Perth, which is 47 millisecond. So obviously the primary metric used is a recovery performance, recovery time. So whenever after a node fail, when it will recover, and again finding a recovery time in these experiments also can be pretty messy, just like for example even finding this distance. There is a ping time a right a metric to be used in our case, that's kind of not very sure, you know. And actually Aaron mentioned about the issue of triangle inequality, which holds to the network distance or not, but it's not always. But you could at least assume that these data centers are connected by very good efficient communication lines, but the modeling them and that matters, I think. So is that clear, the storage context? So once what we do is one of the ways, this is our experimental strategy, how to actually test our ideas. First what we do is that, so what happens with in the previous version of Hadoop, which is Hadoop 2.0, what it does is basically whenever you have a RAID in a file, it starts like an hard data and it is triple replicated. And after when you do enable RAID path for the file path, then for parity blocks, so once you make the triple replication back to 1, then automatically it start deleting the 2 blocks and make some parity blocks. That's how that kind of things working. In the new Hadoop, you can have a RAIDed file straight away, and you could probably make programs work directly on the RAIDed file. But that's how we did the things, and we had to actually use the open source software to do this way. So first one is uploading a file to the triple replicated file, then enable RAID. Then simulate single or double node failure. So once it's all been RAIDed, then you manually go and make these node fail, just like what we did in the demo. And then stopping data node script in the manually, then record repair time and repairing all the lost buffer. So once it is done, once it is repaired, so it will generate all the log files. So you can, by going through the log files, you can actually record various things. So that's not one way. You could, once the experiment is fixed, you could write simple script to actually get this information, but sometimes you need to go to manually, because sometimes you may say about 10 such experiments, you find out the difference. So the getting time is basically visiting the log file and finding out. So the work involved is basically you have to plan all of this. Sometimes running the one full set of experiments will take some hours. So you have to plan very clearly, and then after that note down everything. And so you need to have, it's just like doing any other physical experiments with this. These are all bigger systems, system level experiments. Repair time, and iterate these steps 1 to 4 20 times for all 3 codes. With or without parity replication, and so what we do, and with or without location awareness. So I will explain about the issue of a location awareness in a minute, but for the parity replication and the 2.1 location awareness. So codes will know that okay, some nodes are in that location, because we already explained these two concepts. So this is the results. So for example here, with no replication awareness and no parity replication. So the first results, for example here, the white one, this one looks like a read time, and then the decode time, and this is the wait time. So in some sense, so what happens is, so let us say in the time wise, you start like this at this point. So when there is a repair thing started, so the systems need like a read streams. So it actually sends a lot of parallel processes, because obviously now that particular worker which is assigned to recover from the failed node now needs to start making read to other nodes, required nodes, and as soon as you get a sufficient blocks into the thing. So as I told you, each one is a 64 MB block. It has to read 64 MB from all the nodes, but each time the chunk only comes from 1 MB. So, but it's so you have a read stream. So once this read stream will start making a lot of reads. So once the data comes again here, so this is the time of wait time to read, and at this point this is the wait time, and here then the decoding starts. So, but then there will be a lot of things, and decoding here, and sometimes this work will be over, and then it'll go on, and so all these data will be collected, and we will look at the times separately. So what you notice here is, for example, the wait time. So this is millisecond, and each file is tested for 640 MB file. So a node is failed, and then we look at, and it is done in the experiment that I mentioned. It's about 20 times, and you take the average. So this particular chart shows basically the center one, that's the average, but these are the different distribution of the repair time. So 20 different times. So because when you repair this time, next time the time can be different. So you actually collect all the times and mention this in chart. So the central line tells you the average, and the other the box tells you the distribution of the times. So you can see that so once for this is, for example, for the sorbus, but the moment you have a parity replication, you can see there is some advantage, but you can see that even after with the parity replication, there could be some cases that may be worse than the best case here. You see? Do you see the point here? So for example, the average here is this, the average time for parity replication, average time is here. So definitely the average time for parity replication case is improves, but there could be some cases, for example here the minimum one is actually has a better time than some of this here. So parity replication not necessarily give you the best repair time for all the things, but overall on the average that improves. So here with location awareness with no parity replication, so you can see that with the parity replication, you can see that it's the same times almost. So there is a slight reduction in the average time with location awareness with no parity one. So you know that thing. But whereas with both location awareness and parity replication, we actually gain a lot, right? So this is for the RS, this is for the sorbus, and this is for the MXR. So this is for the RS. You can see that so sorbus is a little better than the RS, and MXR is always better. So you can see that this is what I'm saying. Sorry, with how to interpret this figure is this is actually between RS and sorbus. So what I'm saying is the sorbus code, even though it's a local one, its average is better than the RS, but there could be some cases in RS doing better than sorbus. So that's why when you do these experiments, you will come to know the range of values. Whereas with location awareness and parity replication, there is a slight improvement, and you see the wait times and all have not improved drastically. But for I think for sorbus there is some improvement. For MXR, they're all same. But with both parity replication, a kind of a parity replication from these figures looks not that impressive, but average has improved. So that kind of a. This is single file. Is that clear? Now I think. Yeah.
What is the black dots?
Pardon?
Black dots.
So this is the. So let me. I have to just look at it. Do you know the?
Yeah, no, it doesn't.
I think it could be
Sometimes it is outside.
Maybe it could be some outliers, but I think probably I can the things can be explained with in other graph we'll come to know why this could happen. Sometimes there could be some change in the network characteristics. There will be some results will be way above it. So more, then we will not probably include that one. Yeah, it could be an outlier. Okay.
So from short bus, basically we are not getting any improvement actually. So the time.
Yes. So basically, the SOAR bus, the code was particularly designed for a data cluster in the same location. The bigger one. That's where they showed a lot of improvement. So our initial result was to show that in fact we got a negative result. In SOAR bus really didn't improve that much because in a geo distributed network. So in some sense, we are tending to saying that the RS code actually more or less does better. So you can see that without anything here, some node failures in RS actually is better than the this one. However, because of the LRC and if you made use of the location awareness. So at the moment we really the Hadoop, in this case Hadoop doesn't take into account any aspect of the code. It just treats every node random and places randomly. Okay, and that's where that was the case. Whereas with single node failure, but this is only just to show that with parity replication and location awareness, so makes some improvement. For example, in the location awareness, parities are also added to the local part, and again, not everything. We only replicate once. So if you replicate one more time, you might get more, but then in that case, the overhead is almost equal to triple replication. It's of no point in it. So these are the things. So figure shows an actually average recovery times for 3 cores under assessment up to single node failure. So this is basically for the average one. You can see that average one, you will see that SOAR bus is consistently, this is with no location awareness, with location awareness no parity replication, and with location awareness and parity replications. Okay, so the average recovery times of a course under different settings. So you will see that MXR still does better because at least. So what we found was, since it is the data has to come back from a bigger larger places, so the simplest MXR actually has to do nothing. It's a simply XR, so it helps. So results with 2 node failure simulation. So then here also you can see, for example, this is the read time, decode time, and wait time. So if you look at it here, this SOAR bus code is in some sense performs poorly than even RS, because it has a more time taken to recover is higher. Okay, but except that it's a bit of I think everything is gone up in this case. But over the for example, MXR actually also MXR is consistently better than the other two. So repair times using double node failure, because in the double node failures, then RS can easily do is RS can take up to 4 node failures. So CPU time and bytes read during repair of one node. This chart shows the storage overhead versus CPU time. So you can see that CPU time in seconds taken by the recovery. So for RS takes about 25, SOAR bus a little less, and MXR is one much lesser. And similarly, the storage overhead also in megabytes read, the amount of information read, and so this has directly proportional to the data read, and so obviously the improvement is there. So, even before doing all this, we wanted to understand actually how these codes behave in different situations. So we had the 3 nodes again, and so we can create different type of clusters. In one type of clusters, we can create all nodes to be in the same node, and then maybe ask same questions and see how the system behaves. Or next what you do is you create a cluster made out of nodes from all other things. So you can come up with variations like some nodes here in this one, some nodes there. So the definition of the cluster you could add in a lot of variety. The having all nodes in a particular cluster, that's the simplest thing, because then that will also benefit, because as we see the main thing dominates is the bandwidth and the red during the thing. So we can make the cluster like that. So we totally before even doing that, we started we wanted to understand the behavior of this, and so we made some test clusters. In one case all clusters are in one location, in other case all things are spread out. So that this is about 25 data nodes in each, with a single master located in Tasmania thing. So cluster 1 has all the nodes confined to a single node. So that is the simplest cluster, and we have other variations a little bit, but I do not present all those results here. So the cluster 5 has all nodes distributed across the 5 disparate locations. So cluster 5 is completely random, and the cluster 1 is located in 1. So in both cases single node failure was simulated, just the same process with the node fail, and the recovery times are measured. So you can see the results from cluster 5, the local parities actually bring some improvement in this, but this is the Facebook Hadoop cluster 5 and Sorbus. As you can see that we have for example, this is a reading time. So there is this is actually the results pertaining to individual run of the program. As you can see that the iteration is the number of nodes. This is the 5th up to 10, 15 up to 50 iterations we have done this, and you can see that there is some kind of a drastic thing. Suddenly this particular one at that point of time reading takes such a long time, compared to 0.5 to 2.5. There is no reason we can make out, because out of these 50 things, this one is just an outlier. So there will always be one such thing like that when you do the experiments. One of them does late. So but here the entire result as we obtained is displayed. So this is the second. This side is a Facebook cluster one. This one is a Sorbus one. As you can see that, and also for the comparison, it's more like little bit things. You can see that the read time is almost similar, and the decode time is the average decode time was found to be better with. So in the cluster 5, actually the Sorbus didn't provide any much improvement, but in cluster. So this is results from cluster 5. Then this is from cluster 1. You can see that they more or less they are around 1 point like this only. But this is for the Facebook RS cluster. This is for the Sorbus one, and so these are the simple results there. And we are still kind of we have to repeat these kind of things in modern things. But this is just to show you the things that happen in practice. So for example, when you collect all these results, there will be some 1 or 2 will be outliers, and you can't explain. It could be a lot of transient network problems, things. So this is how the things start. So with these ones, we found that the times for cluster 1 was always better than the times for the cluster 5. So cluster 1, that's because cluster 1 is all located. So that's why this gives you a heuristic. So okay, if at all I have some extra parity blocks, please add it to the same cluster. That might bring the cost down a little bit. So it's kind of adding heuristics. So that we try to, but no one actually tried to actually look at the code properties, what code is there and how to match to this, and that's where some ideas we try to do. So this is called now there is a question, general question come. So we have, so is that clear? So this is a kind of a brief the presentation of some of the results that we got in working with these codes on a general purpose software, like Hadoop. So the next idea was, for example, maybe that I have an RS code now. RS code, to repair a node, it has to contact all 10 of them. So maybe there is not much of a thing. But our MXR code has a different structure, LRC has a different structure. So when you design all these things on a Hadoop doesn't disregard this is the first node or second node. He just needs all the equation pertaining to the whatever for the recovery. Doesn't attach much importance into the where is where, which node is in which place. So, but we did consistently observe that, for example, in cluster 1 where all the nodes are in the same area, the performance is much better than the cluster 5. So, all this gives an idea whether, for example, putting these nodes, taking care of the code locations, code positions. At the moment, your node may know that it is in the same region, but whether which symbol in the code you are placing there, this information, that is information to the location to the code symbol, this was not used, and that is what we call is kind of a placement. Now Hadoop has a general placement strategy. In mostly cases, let's say you have a rack, it will just throw blocks randomly into this, and it doesn't care. I mean, there you remember you are distributing all these things for the purpose of getting some resiliency and reliability, and also and parallelism for the actual work at higher level on that system. So how to know this is a kind of a problem of optimally placing the nodes, so that in the event of a node failure, the system could recover it much faster. I mean, so how do we come up with such a one? So if you look at it, then in the paper that we mentioned by Demakis itself, this is actually considered as an open problem. So coming up with a coding scheme and also the placement strategy such that the repair time is optimized based on that thing, because what we are looking is not like a familiar single cluster, data center cluster where everything is in one place. It's all basically distributed, so you have a different network characteristics. So how to do that? So this is and that's where the network topology plays an important role. And so the problem with this is that network topology may even vary with time. So for example, for some reason, as you see, the system may move blocks from one node to another node. So automatically the topology concerned with that particular code word might change. But it might move probably in the same thing. So if you keep the topology as a general geographical area, so for example, I have 45 nodes. 45 nodes are kept in 3 locations. So then maybe that the topology is only with the 3. So in some other application, topology can be manageable or handleable, but still when you let's say when you are running the same scale, you increase now the number of nodes to 400 or 500, and for a big job, then topology can be complex as well, and so the topology vary with the time and position, and the dynamic nature will influence how the repair cost. Because of that, if it becomes some nodes go to Perth level, and so obviously it has to fetching and everything will be delayed and cost will be more. So what is the way? Is there any way where to place it optimally all these nodes such that to better recover? And that's the problem of optimal placement. So what are our options in that area? Okay. So this is the I mean, before even describing this, I will actually probably mention this problem, and this is again with the hope that mostly if you look at the practical thing, 98% of the node failures is only 98.2, even sometimes even higher is only single node failure. So obviously you have to optimize the nodes to take care of the single node failure. And so here is just a simple example. So for example, we will take a 6-3 code. Okay, so if you all can think about 6-3 code, that is here n and k. So obviously there are 6 blocks. 3 and 3 of them parity and 3 of the nodes, and let us say we have 3 different locations, and say the cost between them is say 3, 1 and 2. So that's a given. So we have been given 3 different locations, and we have to place it nodes. I mean, if you tell the Hadoop to have all this treat as a one rack, then all 6 nodes can be thrown in randomly here. Okay, and you may have say certain nodes available for you or certain nodes available for you. So you may have some other constraints as well. Assume that, let's say because we have a valve that needs to be kept in 6-3 code. So what are the different ways you could do? So maybe you could place 1 here and 2 here, and of course all the other 3 things will go here, right? Okay. So what is the kind of an average cost of repairing? So for example, if this is repaired, so another node, he needs to get 3 more to repair, right? I am just using RS code, right? There is no special thing. It's a simple whatever the code is. So what is the if this is down, then it has to download 3 other more. So maybe if he gets these 2 and this one, what is the cost? 7. But then it can do all these 3, then what's the cost? 3. So from all the possibilities, you obviously can choose the minimum, right? So you can see that there could be many this is what I mean, when you are talking about the computing the average cost. So what you have to do, you have to assume that each one of them can, let us say node in this can fail, node in this can fail, but because now we are grouping all these nodes within the location in the same way, cost of repairing this or this is one and the same. Okay, so you can actually let us say compute the things. Let us say what is the cost for failure in this region is, you can have 7 or 3. So minimum is 3. So with this 3 is minimum 3. What about the cost of repairing node here? So 1 is there, so it can use the 1 local itself, and he can do probably 1 from here, yeah, but that will be increased. Definitely 3 is there, so obviously he will take 2 more from here, so the complexity is 4. Okay, and if a node fails here, he needs to get only 1 more, and probably it's better to fetch from here, so it's 1. So really the average cost for repairing 1 node is how much? It's about 4 plus 3 plus 8 here. Okay. Now we can have a different so same location. So the 3, 1, 2. So here then you may have another combinatorial, another way to place them. So maybe here you place 2 here and 1 here and 3 here again. Okay. So now what is the cost here? So for example, this node fails. What's the cost? So he only get 2. So probably 2 is better. Okay, 2. And if this fails, then he has to get all the 3, 6 here. Okay. If this fails, he needs to get 1 more, and he can get from there 1 here. So what is the cost with this configuration? 9. Okay. So similarly, if you have another cost like this, I mean again, so this I have only summed the cost, but in order to find an average cost, you may think, for example, the cost here, the average cost is actually 1 times 3, 3 times 1 and 4 times 2, and then you sum and divide by 3, you get an average cost. So like that, for a particular configuration, you got other ones, so you may choose, right? So you can apply this combinatorial optimization idea, but how do you come up with the thing is still an open problem. This is there, and we are trying to apply, and it will come up in our future research. We are working on that. So what we do is that then we need to compare with the random placement. So for example, some of this one is a random placement, and some, of course, with RS code, each one the code doesn't differentiate between each one. It's more or less you have 10 parities, 10 data nodes and 4 parities in the normal code. But let us say in 6.3 code itself, so you can now look for this kind of modeling this kind of situation and choose here. So which one do you choose? I mean, maybe this one. But what might happen is this cost whatever at the moment 3 is there, it may go up to say 10 or 11, 12. But so if a solution that is obtained with, say for example here one of them is a very high cost line, and going if the cost go up, maybe the one solution that you have found, maybe it may continue to be the better one. But on the other hand, what might happen is that whatever this, it might become very cheap, it may go down. Also then the actual calculations will change. So you need to actually, so and this is for not just for 2, 3 locations. So maybe if the locations become 5, situation become complicated, but you can still you can try to look at this problem. This is one of the problems that what we are working on. We are taking this into consideration. Okay, that's one thing. So this is the problem, just to motivate the. So if you optimally place them. I mean, at the moment I took an example of an RS code where the position of the code word in the thing doesn't matter, because repairing each one of them involve almost contact any 10 of them, and the number of complexity is almost same. So it's not much of a thing. But for our MXR and other code, there could be different situations. So the solution of this optimization could differ. So obviously in this work what I am going to show now, what we do is that we'll take into consideration of the locality properties of the code, and we will use that to come up with some heuristic that help us to optimize the placement. So we call this as the code aware placement. I mean, if you look at the ideas here, it's not really it's a very simple heuristic. We don't want to get too much of thing, but what we observed with MS code, so we want to just at least we want to identify the structure of the code to the problem. Okay, so here for example you take a MXR code. What we do is, so for example, in the thing, so you have actually it is almost like this, right? B1 to B5. B6 to B7, B10, and these are the 2 parity nodes. That's how the MXR code is. But for repairing say B1 and B6, they are one of the local groups, so we can now tag the symbols with a group. So even though we have totally 17, we can put say into 5 groups, and of course the last 2 global parities can be put in any other. It can be any one of them. So problem is basically how to place them in this. So what we the code aware placement, what we do in location 1, whenever we choose for example B1 in one location, we will force B6 and P1 also in the same location. So if I ask Hadoop to do it randomly, he will throw everything in a random fashion, but now I tell Hadoop and say, okay, when you do with this, you please only put all them together. Then B2 means B7, P2 or all of them. For example, you see wherever B2 is there, then B7 and P2, B7, P2 is there, B5, B10 is there. So you can actually put in the location state. This is one simple location one, but it may be possible that you may have a more, so you have availability of more nodes in a particular location. So you may throw some of them, but whenever you do, you put one, you put the same group. Okay, so now you expect that for example this node is down. Really now repairing it doesn't need to contact other things, it's just local thing itself. Okay, so this is the simplest heuristics that we tried with from our previous. So the previous result was published in one of the conference in a DRCN conference in Paris. So from now that onwards we further improved by just adding this code aware property. So now once you have got the code aware placement of blocks results with a single node failure. So this removes times, for example recovery times of MXR code before and after code aware. So this is basically MXR before code where it had for example, time taken for recoveries are something around for about 4500 millisecond mark. And then after code aware, it has come down to almost about really the improvement is about more than 20 or 30% improvement. And we, that's the decode and wait time. So this is the placement of blocks with code awareness. Okay. Yeah, so you can see that this improves. So further research basically what tells is that at least some of our assumption that the heuristic, that there is a possibility of optimization exists. Now it works. For example, you could take care. For example, in Sorbus, you have how many local groups? There are 2 local groups. So whenever you put one node of a local group, put all other nodes in the same location, and that forces even LRC is also improved. We have results for that as well, but I have not mentioned here. So consistently, this code aware policy has some improvement in it. And so, I mean, for this to implement this policy, we don't have to do a lot. It's just changing a few aspects of the Hadoop system. It's like improving, the systems. Put some of the extra script written there, and in the allocation, so automatically this is taken care of. So further research in this actually, this is a optimization, that is the placement, optimally placing the nodes such that you achieve some better performance for the repair is an open problem, and actually doing it, and we are working on it in that. So also points further on possibility of optimizing based on other properties for coded storage. So in fact, this modeling storage network topologies with different parameters like bandwidth and delay has been open things. So that's another thing that we'll do. And minimum communication needed for repair and erasure code in such context has not been studied also. Like when such thing happen, what's the minimum available? So most of the time when we look at the the bandwidth storage trade-off, all takes care into some general considerations, but not with respect to specific things. So this research kind of is also there, as actually mentioned in the paper by the Dimakis. So this is a kind of a thing that happens with this result. Yeah.
That could be
another dimension. So obviously, what we have done is very simple location here. So obviously, what might happen is, say you have a location 1, which may have there may not be enough nodes there. That may force us to think, or maybe so there will be some things, but on the average, this is always going to add. But if any, what I'm saying is the problem is that this is changing. I agree. Like as I mentioned here, instead of some 3 to something can change. At that time, the cost can go up and down. But what the problem is that in future there are many new concepts are coming, which is called as SDNs. What do you call for the storage? Distribution storage. Software defined networking, and in such case what will the control plane for the network, they have a better control. So when a user or a particular process requests more resources, the control plane takes care of that kind of thing, so that can run this optimization as a part of the that control plane. So and some of these things, whether we have a good solution or not is something to be still proved, but with the computations available, depending on the network topology and the time at that time, this controller can run this and provide the code and the data appropriately. So this can add into further things, but they are all further research. Is that okay? That's a kind of a research in this area for the. So I've actually illustrated the issues in the geographically placing the placement of policies. Yeah. So I have actually looked at the compare the cost. The cost can depend on so many things, right? So really modeling the cost required for a bandwidth or delay is also an open problem, and and that's but that's an ongoing research that can be whatever that is there in the distributed system you can absorb and try to do that. So also what happens is that say another interesting problem you could do is after for example particular node is failed and it gets repaired. Now the new node can be placed in one of the 3 locations, or let us say whatever the locations. So you can even come up with another optimization problem, like after this is repaired, maybe where it is better to be repaired, whether here or there. So that also another question you can do. So the optimization wise, I think there are stall things. That's why actually he kept in the original paper as I think so. And again, what we have considered is for erasure coding. So this is actually for RAIDing. So, but if you can also do for the hot data, that will be pretty interesting case. So having a code for working in the hot data, that's also there. So in fact, some of the candidates that you could use is basically the hitchhiker, that piggybacking framework that I mentioned, that has a possibility because you're not affecting the Hadoop things. You just kind of rely on the same structure and design new codes. So this is what some of this work, and so the next part is to actually show some practical work and things. So we had demonstrated something yesterday with MXR and things.